This is the second of two final exam reviews, and today we're going to review material from exams 1, 2, and 3. First, for exam 1, I would like you to give the electron configuration notation and the electron dot notation for a niobium atom and an iodine atom. Then take a minute, and then we'll give you the answer. For niobium, it's located in the D block on the periodic table, specifically the 4D block. It's the third element over in the 4D block, so that means its electron configuration is going to end 4D3. If you move up from niobium and all the way to the right, you get to the noble gas krypton. So if you have krypton in brackets representing all the electrons up through krypton, the only sublevels with electrons past krypton are the 5s, so it would be 5s2, and then finally 4D3. Krypton has 2 electrons in its highest occupied energy level, which is the 5th energy level, so therefore its dot notation would have 2 dots. For iodine, it's located in the 5p block of the periodic table, and it's the 5th element over in the 5p block, so it's going to end 5p5. If you go up one row from iodine and over to the right, you get to the noble gas krypton, and then the sublevels that contain electrons past krypton would be the 5s, so it would be 5s2. Then the 4D block, and it's filled 4D10, and then you reach the 5p block, so it's going to be 5p5. Krypton has as its highest energy level the 5th energy level, and there are 7 electrons in the 5th energy level, 2 in the 5s sublevel, 5 in the 5p sublevel, and so the dot notation is going to show a dot for every electron in that 5th energy level, and that would therefore be 7 dots. Next, what type of compound would you expect niobium and iodine to form? Niobium is a metal, iodine is a nonmetal, and when metals and nonmetals bond, they form ionic compounds because the metals have a low amount of energy needed to remove their valence electrons, so they easily form positively charged ions, while the electrons are attracted to the nonmetal atoms, and those nonmetal atoms form negative ions. And so when you form positive and negative ions, being oppositely charged particles, they will attract each other. And the attraction of a positive ion for a negative ion is what's called an ionic bond. And so therefore we call these compounds ionic because they're made of ions and attract with ionic bonds. Why don't you take a minute, see if you can draw the correct Lewis structure for the ionic compound niobium-3 iodide. If the niobium is going to form a positive 3 ion, it must lose 3 electrons. The electrons that always get lost first are the ones in the highest energy level. They're the ones furthest from the nucleus and most easily pulled off by some other substance. So the 5s electrons will be pulled off plus one of the 4d electrons. The dot notation, therefore, for a niobium positive 3 ion would have no dots drawn because its 2 valence electrons have been removed, but its charge will now be positive 3 because it's also lost an additional 4d electron. Iodine atoms have 1 spot left in their outer shell in order to complete it and have a noble gas configuration. So if the niobium atom loses 3 electrons to make a positive 3 ion, you would need 3 iodine atoms to each gain one of those 3 electrons, forming 3 negatively 1 charged iodide ions. And so the correct Lewis structure for this ionic compound would show 4 different ions. It would show the niobium positive 3 ion with no valence electrons, meaning an octet in its next lowest energy level, and the iodide ions having 8 valence electrons because they've each gained an electron, creating a noble gas configuration in their outer shell. Let's check some periodic trends now from our first exam. Why don't we see if we can compare the atomic radii of zirconium, niobium, and molybdenum, and see if you can arrange these from largest to smallest. These 3 elements are in the same row on the periodic table, and as you move to the right on the periodic table, the general trend is the atoms are going to wind up getting smaller. So that means the first atom you reach in any row on the periodic table will be the largest one. So zirconium atoms will have to be larger than niobium atoms, and niobium atoms will be larger than molybdenum atoms. What's the reason for that? There are 2 factors that influence all periodic trends. It's the nuclear charge and the amount of shielding. If you're in the same row on the periodic table, you have the exact same number of inner energy levels that are shielding or blocking your outer shell from attracting the nucleus. So zirconium, niobium, and molybdenum have the same amount of shielding. That will have no effect. The only difference is, as you move to the right on the periodic table, you're increasing the nuclear charge. Niobium has one more proton than zirconium, and molybdenum has one more proton than niobium. Those extra protons attract all of the electrons in the atom, even the outer shell ones, pulling them closer to the nucleus and making them smaller. So the general trend on the periodic table for atoms decreasing in size as you move to the right is because moving to the right on the periodic table, the outer shell electrons are attracted by an increasing nuclear charge, while the shielding of the nuclear charge remains the same. This results in atomic radii decreasing. Let's have you answer the same questions for these three atoms. Compare the atomic radii of vanadium, niobium, and tantalum. Atoms of these elements are located in the same column on the periodic table, and the general trend is as you go down a column on the periodic table, atomic radii increase, the atoms get bigger. Why should that be? If that's the case, vanadium being at the top of its column would be the smallest, tantalum at the bottom of its column the largest. Once again, we think about the two factors that influence all of these periodic trends. It's nuclear charge and the number of shielding energy levels. As you go down a column, you're increasing the nuclear charge. That would actually cause the electrons in the atoms to be attracted more strongly and be pulled in, making the atoms smaller. However, the secondary factor, the number of shielding energy levels, increases as you go down the periodic table because the atoms are always adding an energy level. If you have more shielding, that overcompensates for the increased nuclear charge, so therefore with more shielding energy levels, the nucleus cannot attract outer shell electrons as well, and so therefore the atoms become larger. So moving down in the periodic table, even though the nuclear charge is increasing, the outer shell electrons are more shielded from the nuclear charge, and so the atomic radii increase. Let's see if we can answer the same questions involving the periodic trends for ionization energies. I would like you to rank and compare the ionization energies of zirconium, niobium, and molybdenum. The trend for ionization energies in a row on the periodic table is the ionization energies increase as you move to the right. So for these three atoms, zirconium would have the lowest ionization energy, niobium a little bit bigger, and molybdenum furthest to right would have the largest. The explanation for this, same thing that we explained for atomic radii. There are two factors that influence all of these periodic trends, nuclear charge and number of shielding energy levels. If the atoms are in the same row on the periodic table, they have the same number of energy levels. So if they all have the same outer energy level, they all have the same number of inner energy levels. That means their shielding is identical. There's no difference in shielding amongst these three atoms. The only factor that would influence any one of the periodic trends, in this case ionization energies, would be the nuclear charge. And as you go from zirconium to niobium to molybdenum, you're increasing the number of protons in the nucleus, which means that higher charged nucleus is going to hold onto the electrons more tightly, which means it takes more energy to pull them off. So the ionization energies increase. So moving right on the periodic table, the outer shell electrons are attracted by an increasing nuclear charge, while the shielding of the nuclear charge remains the same. This results in the energy needed to ionize them to increase as well. Let's have you compare the ionization energies of vanadium, niobium, and tantalum. These are three elements in the same column on the periodic table, and the general trend for ionization energies is, as you go down a column on the periodic table, the ionization energies decrease. That means vanadium, being at the top of the column, would have the highest ionization energy, then niobium would be a little bit smaller, and tantalum would be the smallest of these three. Why is that? As you move down on the periodic table, the nuclear charge is increasing, which would tend to lead you to believe that the higher nuclear charge would hold the electrons more tightly, causing the ionization energies to increase. However, you're also increasing the number of shielding energy levels, and the increasing number of shielding energy levels overcompensates for the increased nuclear charge. It blocks the nucleus so much more from the outer shell electrons that the attraction is smaller, and therefore the electrons are pulled off more easily, which means a lower ionization energy. So moving down on the periodic table, even though the nuclear charge is increasing, the outer shell electrons are more shielded from the nuclear charge, so the energy needed to pull them off or to ionize them decreases. Let's have you compare the ionization energies of a niobium atom and a niobium positive 3 ion and see if you can provide an explanation for your answer. Of these two, the niobium atom has the lower ionization energy, and the niobium positive 3's ionization energy is higher. Now, why would this be? Let's look at their electron configuration notations. Niobium is located in the 4D section of the periodic table, and as if we try to draw its electron configuration notation, it would be krypton in brackets, 5s2, 4d3. The niobium positive 3 ion would have lost 3 electrons, always losing the highest energy level electrons first, so the 2 5s electrons get pulled off preferentially. And if you're going to remove any more, and you must remove one more if you're going to make a positive 3 ion, the third electron being pulled off would be a 4d electron, so the number of 4d electrons would decrease to 2. So this is what you have to look at to determine ionization energies, because it's a clear difference here. The niobium atom, if you had to pull an electron off of it, would be coming from the 5th energy level. But if you have a niobium positive 3 ion, the electron you'd be pulling off would come from a 4th energy level orbital. And the higher the energy level of the orbital, the further that electron will be from the nucleus, the more shielding energy levels it will have between it and the nucleus, the lesser the attraction. So the niobium atom, having an electron being removed from the 5th energy level, would require a small amount of energy, but the niobium positive 3 electron being removed comes from a closer energy level that's less shielded, and so it's going to take more energy to pull that electron out. So the outer shell electrons of niobium are in the 5th energy level, and they're more shielded from the nuclear charge, so the energy needed to ionize them is going to be less. Let's go on to exam 2 material, and I'm going to ask you to draw the Lewis structures for 3 different covalently bonded molecules, NBr3, XEF2, and HNO, where N is the central atom. Once you've drawn the Lewis structures, I want you to predict what the name of the shape would be for each, and then tell whether each would be polar or nonpolar. First, for NBr3, if you're going to draw the Lewis structure for a covalently bonded molecule or covalently bonded polyatomic ion, you should first count up the valence electrons that will be found in the molecule. The valence electrons for nitrogen are 5, bromines are 7 each, and if you add up the total number of electrons from 1 nitrogen and 3 bromines, that would be 26 valence electrons. We then draw the skeletal structure where we assume the first atom is in the central position and the other atoms are bonded to it. The bonds here each use a pair of electrons, so we're using 6 electrons. Now we're going to fill in lone pair electrons to try to make noble gas or octet configurations for all of the atoms in the molecule, starting with the outer atoms first until we get to 26. So we've already used 6 electrons. This is 8, 10, 12 octet, 14, 16, 18 octet, 20, 22, 24 octet, and now we'll go to the central atom, and electrons 25 and 26 go here, and this configuration gives you an octet for all 4 atoms. This would be the expected Lewis representation for the NBr3 molecule. The steric number of the central atom is 4, 3 bonded atoms, 1 lone pair. A steric number 4 always leads to a tetrahedral array, but because one of the 4 positions are a lone pair, the atoms are arranged in 3 out of the 4 tetrahedral spots, the 3 bromines are, and we call that shape trigonal pyramidal. Because the molecule is trigonal pyramidal, then the 3 NBr bonds are all pointing slightly in the downward direction, and so each of those bonds, which are going to be polar because nitrogen has a slightly higher electronegativity than bromine, each of those bonds will have a dipole moment pointing from the lower bromine up to the higher nitrogen. And when 3 dipole moments are arranged in an array where they're all pointing either in the upward or downward direction, they are asymmetrical. That's going to make a polar molecule. One other way to look at that is if you have 3 dipole moments in a molecule, If they're going to cancel out with each other, the three bonds have to be in a planar array, 120-degree angle between them. So a trigonal planar molecule with an angle of 120 would be nonpolar. The three dipole moments would cancel out. But a pyramidal molecule all has bond dipole moments pointing from the bottom of the pyramid up towards the top where the nitrogen would be. And because they are not symmetrical, that makes the molecule polar. For XeF2, the xenon atom has 8 valence electrons. Fluorines have 7 valence electrons each. That adds up to 22 valence electrons for the molecule. The skeletal structure would put xenon in the central position, and you would bond 2 of the fluorines to it. That uses up 4 of the 22 electrons, so the remaining electrons must go as lone pairs on each of the atoms, outer atoms first, to try to create octets. So far we have 2, 4, here we go. 6, 8, 10, octet. 12, 14, 16, octet. 18, 20, octet. We now have octets for all the atoms, but unfortunately, I still have 2 electrons left over. So when this happens, you have to look for an atom in your molecule that has d orbitals that are empty in its outer shell. And those are atoms that are in the 3rd, 4th, 5th, or 6th periods of the periodic table. And xenon fits that bill. So xenon will have d orbitals in its outer shell. That means it can hold excess electrons. So the electrons 21 and 22 must be fit into the outer shell of the xenon. This causes the xenon atom to exceed the octet rule, but that can happen when atoms have d orbitals in their outer shell. If you want to test this molecule to see if maybe we should make double bonds with those lone pairs, you have to calculate the formal charges for each of the atoms. For the fluorines, the formal charge is calculated by taking its natural number of valence electrons, which is 7, subtracting each bond a fluorine's making, and each bond fluorine's making 1 bond, and subtracting each lone pair electron the fluorine has. They each have 6. So their formal charges are 7 minus 1 minus 6. They both come out 0. The xenon has a naturally 8 valence electrons. In this molecule, it's making 2 bonds, so we subtract 2. And it has 6 lone pair electrons, so we subtract 6 more. 8 minus 2 minus 6 is 0. Because this Lewis structure has 0 formal charges for all the atoms, those formal charges are as low as they can be. This is the best Lewis representation for the molecule. No double bonds are created. For the shape of the molecule, the steric number of the central xenon is 5. It has 2 bonds and 3 lone pairs. 5 groups spread themselves out as a trigonal bipyramidal geometry. But if you have lone pairs in a trigonal bipyramidal geometry, the lone pairs are in their least repulsive positions if they're in the equatorial spots. So if they're taking up the 3 equatorial spots, the fluorines will be locating in the top and the bottom axial positions, making this a linear molecule. The bonds in the molecule are polar. Fluorine has a higher electronegativity than xenon, so you have 2 polar bonds in the molecule, but one polar bond is pointing to the top position and the other is pointing to the bottom. Those 2 bonds are 180 degrees apart from each other. They're in a linear array. And when you have 2 dipole moments in a linear array, they are symmetrical, which means they cancel out. That makes the molecule nonpolar. The last one, I had to tell you that nitrogen was in the central position. If we add up the valence electrons, hydrogen atoms have 1 valence electron, nitrogens have 5, oxygens have 6. There'll be 12 valence electrons altogether in this molecule. Skeletal structure has the nitrogen in the center. We're using 4 electrons to make the 2 bonds. We have 8 electrons left. So 2, 4, 6, 8, 10, and then 11, 12 on the central nitrogen. This gives the oxygen an octet. Hydrogen atoms are stable with a duet because only 2 electrons can fit in their outer shell, which is the first energy level. But this is not a correct Lewis structure because nitrogen does not have an octet. So when this happens, you have to take a lone pair from an atom that has an octet and move the lone pair into a sharing position to create a multiple bond. If we make a double bond in this molecule, the nitrogen now has 8 valence electrons, so does the oxygen. The hydrogen has a duet. This is the best Lewis representation for this particular molecule. The steric number of the nitrogen is 3. It has 2 bonded atoms and 1 lone pair, thus 3. 3 groups spread themselves out in a trigonal planar geometry, but if one of those positions is a lone pair, the shape of the molecule is described by only where the atoms are, and the H and the N and the O would therefore be arranged in a bent array with the trigonal planar angle of 120 degrees. Oxygen has a higher electronegativity than nitrogen, so there's a dipole moment pointing from the end of the O. Nitrogen has a higher electronegativity than hydrogen, so there's a bond dipole pointing from the H to the N. These two bond dipoles are pointing in the same direction, therefore they cannot cancel out. Therefore, this molecule is going to wind up being polar. Now, for the three molecules we've just drawn Lewis structures for, I would like you to take a few minutes and see if you can draw the bond orbital models for all three, labeling each of the bonds in those molecules. First, for NBr3, to draw a bond orbital model, you have to identify what type of hybridization each of the atoms are going to be undergoing, and then you have to know the geometry of those hybrid orbitals. The nitrogen has a steric number of 4. It's going to undergo sp3 hybridization, and sp3 hybrid orbitals are arranged in a tetrahedral shape. So you draw your nitrogen atom with 4 tetrahedral orbitals on it, 1 up, 3 down. And then bromines will bond to 3 of those, and a lone pair will be in the final one. The bromines also have steric numbers of 4, so that means they're going to be sp3 hybridized as well, so you have to draw tetrahedrally arranged orbitals on each of the bromines. The one on the right is the one you should be able to draw perfectly because it's flat on the paper. So if you turn your head 109.5 degrees to the left, you can try to draw a perfect tetrahedron with the bond that was already on the paper as the top bond. You can put 3 lone pairs in here, and that accounts for all the orbitals on the bromine. The other 2 are also sp3 hybridized, but because they're not on the plane of the paper, one is in front, one is behind, just do your best in trying to draw what you'd think would look like a tetrahedron to hold the 3 lone pairs, and what would look like a tetrahedron to hold the 3 lone pairs there. This would be the bond orbital model for NBr3. Now there are 3 bonds in the molecule, and those bonds are an overlap of an sp3 orbital from the nitrogen with an sp3 orbital from a bromine. Those sp3 orbitals point directly at each other, which makes them have perfect symmetry around the internuclear axis, so we call them sigma bonds. And so each bond, all 3 bonds in this molecule, would be called sigma sp3 plus sp3. For the XEF2 molecule, the central xenon has a steric number of 5, which means its hybridization is going to be sp3d. And sp3d orbitals are arranged in a trigonal bipyramidal geometry. So if I arrange the 5 different orbitals, ones pointing up and down are the equatorial or axial spots rather, and the 3 around the middle are the equatorial spots. Lone pairs always take the equatorial spots to minimize their repulsion, and so the 2 fluorines have to go in the axial positions that we had said earlier. The fluorine atoms each have steric numbers of 4. That means they're sp3 hybridized, so you're going to have to draw sp3 hybrid orbitals in a tetrahedral array on each of the fluorines. So here's a perfect tetrahedron using already the top bond as one of the 4 spots with the 3 lone pairs. And if you turn the paper upside down, you can draw a similar tetrahedron for the top fluorine as well. There are 2 bonds in this molecule, the bond between xenon and fluorine. They're a direct overlap of an sp3d orbital from the xenon with an sp3 orbital from the fluorine. And because they're directly pointing at each other, they're perfectly symmetrical. So they're going to be sigma bonds. So the both bonds in this molecule would be labeled sigma sp3d plus sp3. Our final molecule was the one that had a double bond in it, and when you have multiple bonds, double or triple bonds, that's when the pictures become a little bit more complex, because a double bond is a combination of a sigma bond and then something called a pi bond. So you want to start by drawing the 2 atoms that are forming the double bond. The nitrogen has a steric number of 3 and the oxygen has a steric number of 3. That means they're sp2 hybridized. And when you're sp2 hybridized, you have 1 additional p orbital left in your outer shell that is not undergoing hybridization. So we draw the sp2 orbitals in the trigonal planar geometry, and then pointing up and down on the nitrogen is the representation of the 1 unhybridized p orbital. Oxygen would be exactly the same. We just do the mirror image of it so that we can have the sp2 orbitals pointing at each other so they can overlap to make a sigma bond. So the 1 bond between the N and the O you see right now would be a sigma bond, an overlap of an sp2 orbital from the nitrogen and an sp2 orbital from the oxygen. The reason that these two atoms form a double bond is that the p orbitals that are pointing up and down will slightly overlap on the top and the bottom, creating a second bond. That bond is not perfectly symmetrical around the internuclear axis. It's only symmetrical on a 180-degree rotation, so that's called a pi bond. And because it's made from the p orbitals, that's called a pi, 2p plus 2p. The p orbitals in nitrogen and oxygen's outer shell are in the second energy level, so they're called 2p's. The nitrogen has two orbitals left. One's for a lone pair, the other's for bonding to a hydrogen. And the oxygen has two orbitals left over, and from the Lewis structure, you can see those are for holding two lone pairs. So the bonds in this particular molecule, first the bonds between the N and the O, there is a sigma, sp2 plus sp2, and a pi, 2p plus 2p. There's one more bond between the nitrogen and the hydrogen, and that bond is an overlap of an sp2 orbital on the nitrogen and a 1s orbital on the hydrogen, and that would be the bond orbital model for that particular molecule. Let's go on to test 3 material, where we were talking about solids and liquids. And I'm going to give you a specific classification of matter, and I want you to tell me what the major interparticle attractive forces are if you have a crystal of this particular material, and then what are the 2 factors that affect their strengths. The first one is ionic matter. Take a couple minutes, then come back and listen to the answer. Ionic matter is any matter created out of positive and negative ions. This naturally occurs when metals and nonmetals bond to form something like sodium chloride or magnesium sulfide. So what holds these positive and negative ions together would be considered the major interparticle attractive force in ionic matter, and those are called ionic bonds. There are 2 factors that influence the strength of ionic bonds. Most important one is the ion charges. The larger the charges of the ions, the stronger the attraction between the oppositely charged ions, and if you have a stronger attraction, that causes the melting point of these crystals to increase or be higher. The secondary factor, which is not as important, but it's important if you wind up having 2 different ionic compounds whose charges are the same, is the sizes of the ions. Because if the positive and negative ions are smaller, they can get closer together, and oppositely charged electrostatic attractions increase as the distance gets shorter between the particles. So the smaller the ions, the closer their distance, the greater the attraction between the oppositely charged ions. Let's answer the same questions for metallic matter. This would be any matter that's made up of only metal atoms. And if you have a chunk of a metallic material like pure gold, pure copper, pure iron, it's millions and millions of atoms, and the attractive forces between those atoms are the sharing of their valence electrons in a delocalized fashion amongst the millions and millions of atoms. We call that metallic bonding. Now, what are the factors that influence the strength of metallic bonds? The most important factor is how many electrons contribute to the bonding molecular orbitals that are delocalized amongst the millions and millions of metal atoms. So the greater number of net bonding electrons that go into the molecular orbitals, the stronger the attraction will be for those negative electrons to all the positive nuclei. And on the periodic table, we see this trend bearing out as you move from left to right. In the metallic part of the periodic table, as you move from left to right, each column moving to the right increases the number of valence electrons or electrons used for bonding by 1. And so as you move from column 1 to column 2 to 3, 4, 5, and 6, you reach column 6 where the atoms have the 6 valence electrons contributing to the bonding of the atoms in bonding molecular orbitals. So the strength of the metallic bond increases from group 1 to group 6. As you go past group 6, the additional electrons that are being used for going into the molecular orbitals are now going into anti-bonding orbitals, and so therefore they decrease the strength of the metallic bond. So there's a pyramid effect across the periodic table for strengths of metallic bonds based upon net number of bonding electrons, low at the left side, peaking at column 6, and then decreasing as you move to the right side. The secondary factor, which comes into play if you're comparing metals that have the same number of net bonding electrons, is the size of the metal atoms. Because if the metal atoms are smaller, that means the molecular orbitals they're creating are going to be smaller, which allows the bonding electrons to be closer to the nuclei. So the smaller the atoms, the smaller the molecular orbitals, the closer bonding electrons will be to the nuclei, and the stronger the attraction those electrons will have to the nuclei of the atoms. So given the same number of net bonding electrons, smaller atoms will wind up having stronger metallic bonds and therefore higher melting points. Let's have you answer the same questions for nonpolar molecular matter. This would be any type of matter made up of nonpolar molecules. So specifically, it means nonmetals, and it's any nonmetals that create molecules that happen to be nonpolar. It could be an elemental substance like oxygen, or it could be a compound like methane, CH4. Both those are nonpolar molecules. They would fit into this category. What are the attractive forces between the molecules? They're not covalent bonds. Covalent bonds hold together one molecule. Interparticle attractive forces or intermolecular attractive forces means what are the attractive forces between different molecules. And when you have nonpolar molecular matter, there's only one. The molecules attract by very weak London dispersion forces. And there's one important factor that influences the strength of London dispersion forces that you should know. And that is the more total electrons a molecule has, the more it's able to polarize the electron clouds in neighboring molecules, creating stronger instantaneous dipole moments, and that makes a greater attraction between the molecules. So for nonpolar molecular matter, the greater the total number of electrons molecules have, not valence electrons, but total, the more strongly they attract each other, and so they have stronger London dispersion forces and therefore higher melting points and boiling points. Let's have you answer the same questions for polar molecular matter. These would once again be groups of nonmetals that bond together covalently to create molecules, but the molecules have a polar character to them, maybe something like HCl, where the hydrogen end is positive and the chlorine end is negative, or water, where the hydrogen end is positive, the oxygen end is negative. When you have polar molecules, there are two attractive forces between the molecules. One are the London dispersion forces, which exist between any pairs of molecules. But if you have polar molecules, they also have dipole-dipole attractions, which is the natural attraction of the permanent positive end of one polar molecule to the permanent negative end of another. Polar molecules can sometimes have a third attractive force called hydrogen bonding, but those molecules must have a hydrogen in its formula, and they have to be bonded to either a nitrogen, oxygen, or fluorine. If that's the case, then a hydrogen in one molecule would be able to form hydrogen bonding with an N or F in a neighboring molecule. Now, what affects the attractive forces between groups of polar molecules? It's the same thing that we talked about for nonpolar molecules, because it's the London dispersion force that varies the most from one molecule to another, and it's affected by total electrons. The more total electrons a molecule has, the more it's polarizing to its other molecules, the greater the instantaneous dipole moments that are created, so the greater the attraction between the molecules. Test 3 also dealt with solutions, and we'll do a final couple of examples with the colligative properties of solutions. First problem, 30.0 grams of glucose, molar mass 180 grams per mole, are dissolved in 100.0 grams of water at 25 degrees Celsius. For water, its boiling point is 100.00 degrees Celsius, T sub B is boiling point. Its K sub B, molal boiling point constant, is 0.51 Celsius degrees kilograms per mole. Its freezing point, T sub F, is 0.00 degrees Celsius. And its K sub F, its molal freezing point constant, is 1.86 Celsius degrees kilogram per mole. First question, calculate the solution's boiling point. So if you can use our colligative property equation for boiling point elevation, take a couple minutes, try to calculate it, and then we'll show you the calculation. A colligative property for boiling point allows you to calculate how much water or any solvent's boiling point will increase. And that's abbreviated. Oh, we're going to give you three things to do actually here. We're going to calculate the boiling point and the freezing point. So sorry for not listing both of those. If I might want to pause again and give you a chance to do the freezing point, then we'll show you both calculations. So to calculate the boiling point of a solution, the colligative property equation for boiling point allows you to calculate how much water or the solvent's boiling point will increase. That's abbreviated delta T sub B. It equals a experimentally measured boiling point constant for whatever the liquid is. In case we've got waters here, 0.51. M stands for the molality, so you'll have to be able to calculate the concentration unit of molality. And I stands for the number of particles that the solute dissociates into when it dissolves in water. Our solute is glucose, which is a covalently bonded molecule. And although it does dissolve in water because it can hydrogen bond to water, it does not dissociate or ionize into ions. So any substance that does not produce ions in water solutions termed a non-electrolyte, and its I value is 1. So we know the I value. We know water's K sub B value of 0.51 Celsius degrees kilogram per mole. We have to calculate the molality of the solution, which is defined as moles of solute per kilogram of solvent. So if we have 30 grams of glucose, we'll need to calculate how many moles of glucose there are, and we'll do that by using glucose's molar mass, arranged so the grams of glucose cancel out. And to 3 significant figures, we would have 0.167, or with a guard digit, 0.1667 moles of glucose. To get molality, you divide the moles of solute by the kilograms of the solvent, and 100 grams of water is 0.1000 kilograms. So dividing the moles of glucose by the kilograms of water will give us our molality, and this comes out 1.667 with a guard digit, molal and glucose. So we now know all 3 values for our colligative property equation, so we can calculate the change in the boiling point by multiplying water's molal boiling point constant of 0.51 Celsius degrees kilograms per mole by the molality, which if I write it out explicitly is 1.667 moles of solute per kilogram of solvent, and then multiply by the Van't Hoff factor, which is a counted number, so not used for significant figure determinations, of 1. This, if you multiply it out, will give you a 2 significant figure value because of the 0.51 was only 2 significant figures. And all the units cancel out except for Celsius degrees. So we get a change in the boiling point of 0.85 Celsius degrees. So water's boiling point, if you dissolve 30 grams of glucose in 100 grams of water, its boiling point will go up by 0.85 Celsius degrees. So to actually answer the question, you need to know water's natural boiling point, which is 100 degrees Celsius, add 0.85 to that, and because both numbers here are 2 places past the decimal point, my final answer will be rounded 2 places past the decimal point, so it's 100.85 degrees Celsius. To calculate the freezing point of the solution, we have a similar colligative property equation, only now this equation allows you to calculate how much the freezing point of the solvent goes down when something's dissolved in it, and that equation is delta T sub F equals K sub F times M times I. The molal freezing point constant is an experimentally measured value for the solvent. For water, it's 1.86, so you can see the freezing point constant is different than the boiling point constant. Dissolving something in water causes the freezing points and boiling points to change different amounts, so different constants. The molality we've already calculated before, so I know that's 1.667, and the I value is still 1 because glucose is a non-electrolyte. So we can now really easily calculate the change in the freezing point by multiplying the freezing point constant by the molality times the I value. In this case, our freezing point constant is 3 significant figures and our molality is 3 significant figures. And so our final answer will be rounded to 3 significant figures. So I get 3.10 Celsius degrees. The colligative property of freezing point depression is that a solute lowers the freezing point of the pure solvent. So water's natural freezing point of 0 will go down by 3.10 degrees Celsius. And when you subtract these, because both of those are accurate 2 places past the decimal point, you'll get an answer 2 places past the decimal point. So the freezing point of this solution is going to wind up being negative 3.10 degrees Celsius.